Good afternoon, ladies and gentlemen, and you're all very welcome to our webinar this afternoon, Yara Fertiliser, tried, trusted and fully traceable. My name is Eva Ross, Head of Commercial Partnerships in Ireland, and I'm delighted to be joined by my colleagues Philip Cosgrave, our Crop Nutrition Agronomist, and John Dooley, our Crop Nutrition Account Manager. Now, we decided to host this webinar because now more than ever, it's vital that farmers are able to make the most of the fertilizer that they're spreading. We see a decrease in fertilizer, partly due to the fertilizer database being implemented in the Republic of Ireland. And so whatever a farmer is spreading, it's vital that they are able to make the most of that. There's also different fertilizer products out there now on the market, and it's very important to know exactly what you are buying and to ask the various questions when you go to purchase your fertilizer. Yara Fertiliser, we were founded back in 1905, and for the Irish market, over 95% of the fertiliser that we bring into the Isle of Ireland comes from our own factories, and they are dotted on the map here. You'll see that our MPKS products, our Complex Compound Fertiliser products, they come from Porsgrunn and Glomfjord in Norway, and then we bring in our nitrates and our urea plus sulphur grades from Sluiskil in the Netherlands, Tertre in Belgium, and Rostock in Germany. Now, of that fertiliser that comes into Ireland, we have two import points, one in Belfast and one in Ringaskiddy in Cork. And we've got terminals at both of those sites. We also then have another terminal at Moira in Northern Ireland, and then we've got a satellite store then in Roscrea in Tipperary. We've got full control then of the fertiliser from the factory, so from production, as you'll see there on the right hand side of the slide, through to seed transport, bagging facilities, road transport, through to the distributor, co-op, private merchant, also the farmer, and then right through to the farmer. I'd also just like to point out that not only do we sell solid fertiliser, but we also offer soil testing at our Pocklington site outside of York. We also offer agronomic advice. We also have our Yara Vita foliar micronutrient range, and they're produced, again, similar to the soil testing outside of York in our Pocklington site. And then we also then offer our digital tools, our Yara N sensor and our Yara N tester that you can see here in the photograph on the slide. So there's a number of demos that my colleague John Dooley has put together for today's webinar, and we're just going to take a couple of minutes now to see the first one. It brings us through the different strengths of fertilizer and why it's important. So I'll hand it over to John there to give the demo.
Hi everyone, John Dooley here from Yara Ireland. Today I'm here to show you about the strength test using this tool. The whole idea of it is we have a mark here from 1 to 10 and we want to see how strong the granules are of our Yara Mila New 18s versus a competitor's blend. So first up, we'll put some New 18s into this tray here. Scatter them about. You can see it's set up here, so pick out the first granule and slip there. We'll try another one. Reset the machine. Boom. 10. Excellent score, what we want to see. Reset it again. 10 again. Perfect. That's exactly what we want to see, guys. A good strong granule that'll go through the hopper, go past the veins without imploding. So we'll just put these back into this. Quickly pour in an equivalent product, and this is in a urea blend. See there, all the different ingredients in it, all the different raw materials, all mixed up, and variations. So we'll scatter them about on the tray here. We'll reset this guy. We'll pick out a granule of this kind. 4. We'll pick out this guy here, a different color of one of the raw materials. 10. We'll reset. We'll go for another different color. 10. And we'll just go back for another different color again. Five and a half to 6. So straight away we can see a variation between a CCF and a blend. That will lead to segregation. It'll lead to product going at different widths through the spreader, and it also leads to weakening down, so where we might see a lot of dust product imploding when it hits the veins because it's not strong enough.
Thanks very much, John. John recorded that video for us a number of days ago, so very much appreciated, John. We'll now hand over to our agronomist, Philip Cosgrave, who will take us into a more in-depth take on our Yara quality fertilizers. So, Philip, over to you.
Good afternoon, everyone, and thank you, Eva, for that introduction. I'm going to cover on my slides a number of different topics. What are complex compound fertilizers? So just to go into that in a little bit more detail, an important element of, I suppose, ensuring that your fertilizer is being evenly applied is tray testing, then looking at the components of fertilizer quality, and then looking a little bit about avoiding risk and the cost associated with your fertilizer purchase. So to start with, just going to go through complex compound fertilizers, and I suppose what are complex compound fertilizers? Basically, with a complex compound fertilizer, every granule or prill contains the same analysis, and every nutrient has the same number of landing sites across the whole field, and every bag is fully traceable from farm to factory. And this applies to our products, our NPK products, our can with sulfur products such as Axan and NutriBooster, but also our Yara Vera product, which is Amidas, which is our urea with sulfur product. So all of those products, they're not a blended product, they're a CCF. So all the nutrients that are supposed to be in those products are all in each granule or prill. And this is just a look at what they might look like. So on the left-hand side, we've a number of different pictures there. We've 6 pictures kind of showing what blended products look like. So a blended NPK generally has a couple of different colors, granules in it. It could have anything between 3 and 5 different colors in it, and there'll be different shapes and sizes as well. And on the right-hand side, this is, I suppose, what our products look like, our Yara Mila products. So these are NPK products. So you'll see that they have similar characteristics, same color, but same physical characteristics as well, and shapes and sizes. So just to go on now about tray testing and to cover tray testing, because, as a farmer applies this fertilizer, how can they ensure that, number one, that their fertilizer spreader is applying it evenly? We also can call this the lateral distribution of the fertilizer, but also that the product that they're spreading can be spread accurately and evenly. And to assess that, we can tray test the fertilizer. So tray testing means that you set out a number of different trays on the ground. If you were spreading to 24 meters, you would put 23 trays in a line across the ground. And there's a process you need to go by to ensure that you do this correctly. But it's basically to ensure that the spreader and the fertilizer is being applied evenly. And then each tray then is emptied into a tube, and you can see that in the second picture there below the tractor and spreader, and that can give you then, when you have all the trays emptied in, it can give you a kind of a visual assessment of how evenly the fertilizer was applied. across the 23 trays if you're spreading at a 24 meter working width. But you can also do, I suppose, it's more detailed, where you actually calculate a coefficient of variation. This is, I suppose, a statistical calculation you do to ensure that your fertilizer is being spread evenly. And to do that, you need to weigh the contents of each of those tubes and to calculate that coefficient of variation. And I suppose if we look at the coefficient of variation and what that means, if we get a result that's looking at 10% or less, we would say that that's a very good fertilizer spreading pattern. So the lateral distribution is quite even. The lower, the better. But generally, if it's below 10, it's good. If it's between 10 and 15, it's good. And if it's between 15 and 20, it's said to be acceptable. But the upper range of that near 20, it's getting, I suppose, where you're going to end up going to be issues with the effectiveness and the use of that particular fertilizer. And if we say that if we go above 20%, well, then there's definitely going to be a yield lost from the application of that fertilizer if it's been applied with a CV of greater than 20%. I suppose an important point to just say at this point, to say now, is that that it's with a Yara product, with a CCF product, you know, once you see if there's a good coefficient of variation, if it's less than 10%, that means that each nutrient within that product has a CV of less than 10% as well. But if we're applying a blended fertilizer, a blended NPKS fertilizer, for example, the whole product, as you look across the tubes, might be quite even, but it's not. The devil is in the detail. It's not until you actually look at the nutrient distribution or the component distribution in every tube, you can see that a good overall coefficient of variation for a fertilizer product can mask a very poor coefficient of CV for an individual nutrient. So on total, the product might be applied quite evenly, but the individual nutrients, so the nitrogen, the phosphorus, the potash, or the sulfur, might have a very high CV. So that's something to watch out for when you're doing a tray test with blended fertilizers. And typically, that is on the bottom left-hand corner or the bottom right-hand corner. That's you know, I suppose a spread pattern over the working width, over say a 24 meter working width. So what characteristics, you know, of a particular fertilizer are important, you know, so that you can end up with a good CV. Obviously, the fertilizer spreader needs to be working, but fertilizer quality has an important part to play in this as well. And I suppose one of the first things we look at is the bulk density, and that's the weight of a fertilizer for a given volume. So usually it's calculated in kgs per liter. So if we look on the left-hand side, we have urea, which would have a low bulk density, and that has a bulk density of about 0.75 per kgs per liter. And on the right-hand side, then the bulk density then of say CAN or Yara CCF products is looking at somewhere like maybe 1 kilo per liter, or a little bit over that. And the higher the bulk density means that it's easier to throw. So I suppose what we're looking at here is we're looking to demonstrate that visually, in that if you have a ping pong ball or a table tennis ball, it is the same size as maybe you know, a golf ball. But if you go and try and throw the golf ball and the ping pong ball with the same level of force, you will throw the golf ball a lot further than the ping pong ball. So that's just, I suppose, a good way of illustrating the difference in bulk density and how it matters when it comes to fertilizer quality. Size range is the next thing, and this is the actual diameter, the average diameter size of the actual granules or prills in the fertilizer. So we would like a kind of a size range between 2 millimeters to 4.75 millimeters. Now, the bigger the particle, or the if we have more particles in the 3.3 to 4.75 millimeter range, then those particles are going to be easier to throw. It's a bit like throwing a very small little pebble or a little stone and then a larger stone or larger rock. You're going to throw that rock further than you would a little pebble or a small little piece of grit or something. So that's you know, an important element too, is that size range. And with the Yara products, a greater proportion, so nearly 2/3 of the fertilizer will be made up of that 3.3 to 4.75 millimeter range. So this is something looking at that's from an Amazon fertilizer spreader publication. So it's looking at the flight characteristics of individual fertilizers at the same spreader setting. So this is looking at, you can see the green line. So if you have a spreader set up and you put CAN into it first, so if you put CAN into it, you will see that the overall, the average distance that the particles will travel will be greater. If you put then a kind of a good quality urea, so basically the fertilizer is dropping into the same point onto the disc, and the discs are moving at the same speed, and the veins haven't been changed. So you can see even at the same spreader setup, you can see that good quality urea doesn't travel as far. And that's because of both the size and the bulk density of that product. But you can see, I suppose, worryingly, the fine urea, so the urea with very fine particles with an average diameter size of 1.9 millimeters, you can see how far they go, or how, you know, the difference between them and the better quality urea or the CAN, for instance. So that's, I suppose, an indication of how the size of the particle and the bulk density have an impact to play on how the actual fertilizer can be applied. So you can imagine if you have products then with different bulk densities, different sizes, how it's more difficult to spread them evenly over the full working width. And the working width is the width that you're working with. So if you have 24-meter tram lines or whatever the distance between the center of the tractor to your next bout, that you're traveling to the left or the right hand side. But it's not the same as the spreading distance, which will always be, generally will be always greater than the working width. So this is the optimum spreader settings then for different fertilizers. So taking the same fertilizers again, we can see where the actual the setup has been changed to optimize each product. But we can see where I've highlighted it with the red circle, if you have the average landing sites occurring at kind of the same area or the same distance out from on the left and the right of the back of the spreader, you can see that the actual discs for the CAN product are traveling at 25 meters per second. But for the coarse urea, the better quality urea, they were traveling at 40 meters per second. And for the fine urea, they had to travel at 100 meters per second. So this then, you know, follows through to the actual hardness. If the spreader discs have to travel, you know, are rotating quicker, well, then they're going to put the actual particles under more pressure. So hardness is a really important characteristic of fertilizer as well. So it needs to withstand, you know, handling, the impact of the spreader vanes, and especially the impact of the spreader vanes at wider spreading distances, and where the actual granules or prills break up. Obviously, you can't really spread dust accurately, so you've got these less predictable spread patterns. So we can see here, you know, a Yara granule, you know, it's the right hardness. We've got control over the manufacturing process and the quality of the physical quality characteristics of our fertilizer. The same with the Yara prill. It's a good size prill. And also then, if we kind of compare this then to what would be in a blend as a phosphorus source, so that's a DAP prill, which can be very prone to shatters, particularly at those wider distances. So another characteristics is the shape of the actual granules or particles. So a rounded shape allows for more predictable movement off the spreader vane. So generally in blends, the potash source or the potassium source is going to be muriate of potash. And we can see that's a crystal, it's an angular fertilizer, angular granules, versus a Yara product, which will have rounder granules. So when each of those are being I suppose the movement of them on the veins of the fertilizer spreader, generally the rounder the granule, it's going to be more predictable. But when you mix in MOP with other constituents, it can influence the actual characteristics of that potash, the spreading characteristics of that potash. And segregation, this is, I suppose we see this with coarse rations. We see it with TMR diets where we put in different constituents in and we mix them up, and then when they're being fed out, then we can see where, depending on whether it's the beginning or the end of the actual feeding out of an actual load where we're feeding TMR or in a coarse ration, we will see that the constituents will vary. And this is something that happens with fertilizer as well. So on the right hand side, we see a kind of a CCF product. So there's no segregation can happen in that because the nutrients are contained in each granule. So there's no segregation, no risk of segregation. But on the left hand side there, you can see where you have a blend of the same nutrient analysis where you have urea, DAP and MOP. So DAP for the phosphorus source and MOP then for the potash source. But we can see then as that's piling up, say if that's coming off a conveyor or it's being emptied out of a mixing unit, we can see that straight away we can see that the in different parts of the actual of the pile, we can see that there's this demixing due to different bulk densities and sizes of the blended components. So at the bottom of it, we'll have a different analysis to the top of it. And that's, I suppose, an important thing to bear in mind during, the handling, the transport, handling and storage of products and when they're being emptied into the actual fertilizer spreader. So this is just looking at the actual fertilizer spreader and what happens when I suppose the smaller particles with a blended fertilizer, the smaller particles tend to rush first. So they rush down and they usually are spread first, and the larger particles stay at the top, and you get this kind of bridging effect. Whereas with a Yara CCF product, this segregation can't occur. So if we look at, I suppose, the composition of these different types of fertilizer, so whether it's our blends or whether it's our CCF products. So for blends, for I suppose products out there that are made up of blends, the constituents of different physical characteristics, this leads to component segregation, to uneven spreading patterns, and the incompatibility of constituents. And particularly with urea blends, which have become more common in the last couple of years, where basically urea is being used as the main nitrogen source instead of CAN. And then obviously there's going to be fewer landing sites as well of the nutrients per meter squared. And we can see this in this little schematic here, where the urea and the lighter, smaller granules are not going to spread as far, whereas the DAP and the SOP are going to spread further. And if we look at, I suppose, what a CCF fertilizer, there's no segregation. Particles have similar spread patterns because of those physical characteristics. And then you have the maximum number of landing sites per nutrient. So you don't have this issue with, I suppose, individual nutrients being unevenly applied over the working width. So this is just looking at that point of landing sites. So this is a comparison of a CCF product, Yara Extra Grass, Yara Mila Extra Grass, and a blended equivalent. And this is kind of compared on if we were applying 2 bags of these products per acre, or 225 kgs of the product per hectare. So if you kind of work that out, that means that if you're applying 2 bags to the acre, there should be 22.5 grams of fertilizer going on per meter squared. So if you count out, I suppose, if you weigh out 22.5 grams of extra grass, it comes to roughly around about 500 granules. But if we just look at the phosphorus, because we know phosphorus is not a very mobile nutrient in the soil. And if we pick out phosphorus in a blended product, phosphorus is usually going to come from DAP. And if we were to measure out, I suppose, how many DAP granules to give us that how many DAP granules are landing in that meter squared. There's only around about 50 granules of phosphorus landing per meter squared. So there's 10 times more P and K landing sites per nutrient with a Yara Mila CCF in comparison to a blended NPK. And this is something, I suppose, which is important to point out. A German study, there would have been very few. I think this might be the only study which looked at working, I suppose, the wind effect on the spreading fertilizer and how it impacts the coefficient of variation. So this is looking at a 21 meter working width, not particularly wide, and at winds of 4 meters per second, which is around about 15 kilometers per hour. And this was done by Professor Randall in Mannheim. And if we look at the spread patterns, for a urea with a kind of a lower size range, there was a CV of 34% with that particular product, where the actual granules were quite small. Whereas the urea that had kind of larger granules, the CV with wind speed of that 15 kilometers per hour, they calculated a CV of 26%. So this is all from my earlier slide saying that, you know, anything greater than 20%, it means that there's going to be yield loss and considerable yield loss. Whereas for when they looked at CAN, which is that high bulk density, higher granule size, even with those 15 kilometer an hour winds, the CV was down at 7%. So that's, I suppose, an important thing to point out about I suppose when we're spreading these fertilizers, that blends particularly that have urea in them, are prone to inaccurate spreading if there is, you know, if winds are any greater than 15 kilometers an hour. And you could say that actually you should be spreading them with lower wind speeds than that from looking at this particular information. And this is just finally kind of looking at this risk, the financial risk. So where we've calculated that the value lost on a first cut, if we just look at a first cut using urea blended NPK, that if you, you know, this is, I suppose if we go with that, I suppose a cheaper product, that urea blended product, at 80 units of nitrogen per acre, and then with also some slurry as well to make it up to 100 units of nitrogen per acre, we're looking at a 5% yield loss in that scenario. And that's roughly, if you look at, I suppose, the replacement value of silage, or we're looking at around about a 15 euros of a yield loss there per acre. Now, what's that? So for if you're using that blended product, you're saving about £3 or €3.30 per acre on fertilizer, but you have a yield loss of 15 euros. And that's probably a conservative estimate of 15 euros because it's not taking into account about the inaccurate application of the phosphorus and potash. It's only looking at the inaccurate application or the uneven application of the nitrogen in that urea blended product. So there is value. That Yara, you know, Mila product, that NPK product is likely to be a little bit more expensive, but certainly, you know, when it comes to the value you get out of that when applying it, you know, you're certainly going to have, I suppose, optimizing yields in comparison to going for a cheaper product. If we look at striping, it was a big, I suppose, last year, there seems to have been a lot of issues with striping, particularly with urea and ammonium sulfate blends. And if we look at a first cut at 80 units of nitrogen per acre, we calculate that, you know, that a grass yield loss of 15%. If you see visual striping, you're seeing, you know, about 15% yield loss there, and that has a value of about 45 euros per acre in lost grass. So for saving, for buying a urea and sulfur blended product, you're saving maybe €2 per acre, but I suppose the risk is that you're losing 45 euros in grass value. So it's certainly worth keeping that in mind when you make your fertilizer purchases over the coming weeks and months. So I suppose finally, to sum up, it's important. I suppose fertilizer is a very costly input on farms, but I suppose it's more important to get the value out of that fertilizer, that investment. And considering that a lot of these blends, particularly those NPK blends, are probably between, you know, maybe 20 and 30 euros per ton more expensive. There is probably on a full load of, on a 28-ton load of fertilizer, you potentially you could be saving maybe 800 to 850 euros per load. But you have to look at, I suppose, when you have to apply that fertilizer, what the potential loss is in actual loss, whether you're growing grass or an arable crop, what's the potential loss there? When you're buying a Yara CCF product, that it's a quality product, and it can be applied evenly, ensuring that there's maximum landing sites per nutrient, but those nutrients then are being applied evenly across the working width. So with that, I'd like to finish up, and thank you for your attention.
Thanks, Philip. We are now going to have another video by John looking at the different particle size of fertilizer.
Next up today, I'm going to discuss the sieve test here to show the consistency, size and granules. What we want to see is 80% of the granules in the 2 to 4.75 region here. So we'll fill this up and we'll give it a shake. First up is the 18s. We put this in here for ease of filling up this. As we can see, we've ended up with between 40% and 50% in both of these brackets. Minimal up here in the 4.75 and practically none in the under 2. Shows you the consistency of granules. Next up in the sieve test is the equivalent in a blend. So make sure at the right end, fill it here. Water level. Put our lid on. Give it a shake. We can see the results here. So between 5 and 10% have fallen into under 2s, over 50% in the 2 bracket, just over 40 here, and just under 10. Clear difference in granule sizes. Next up, we're going to demonstrate the difference then between a urea and a CAN-based product. This here is CAN plus sulfur, or Axan, Yara Axan. So we'll weigh the empty cylinder again to demonstrate. 0.26. We'll tear this. Come over here. We'll wear the Axan. 1.01. So a clear difference. The urea reading already at 0.62. A clear difference between the two products in bulk densities. These will travel a much greater distance than the urea. But secondly, if these two products or similar products are mixed together, this is where farmers can run into a lot of problems with uneven distribution of the nutrients, leading to all sorts of striping and very noticeable patterns of uneven distribution. Next up today, we're going to demonstrate the differences in bulk densities. In this cylinder here, we have normal 46% straight urea, and this one here, we have our Yara Amidas, 40N, 5.6% sulfur, the only CCF urea with sulfur available to the Irish farmers. The 3 cylinders here in front of us are all exactly the same, and before we fill them up, we check their weights, which are exactly the same. I'll demonstrate here now. We're on 0. .25. So I'm just going to tare that. We'll weigh the first cylinder with urea. There's a reading here of 0.62 kilograms per litre on that. So we'll zero it. We'll go back and we'll do exactly the same again. The cylinder, 0.25. Tare it. And now we'll show the bulk density of the Yara amide. 0.73. Clear difference in the bulk density of the granules, leading that our Yara amide would spread a lot better than a normal urea, both suitable for grassland and arable farmers.